Hello, my curious friend, and welcome to Deep Field Channel. Tonight we will stroll through one of the most elegant secrets nature keeps hidden in plain sight, as the English would say, right in front of us, every day, everywhere the eyes can reach. We will explore why the universe seems to have a profound, almost philosophical allergy to anything that dares to be perfectly straight. A sort of silent conspiracy against the straight line that crosses galaxies, rivers, bones, beams of light, and even time. I promise to try not to make the subject so fascinating that it drives sleep away. But this theme has a beauty that insists on revealing itself slowly, like mist over still water. But before we begin this gentle journey, I would love to know in the comments from which corner of the world you are listening to me tonight. And if laziness has already reached you before you do, just leave a simple hello. This small gesture tells YouTube that this space is welcoming, that there are people here who like to think slowly and sleep well, and that helps us bring more tired minds to relax with us. If you appreciate our journeys through science, also leave your like and subscribe to the channel. And to you who are already part of this community, who have spent other nights here with us, my most sincere thanks. Now, wherever you are, find a position that your body accepts well. Just float with my words. And if sleep appears before the end, accept the invitation without any guilt. Let's begin. Think for a moment about how you got to bed tonight, the path your feet took across the room, the trajectory your arm followed to reach the blanket, the arc your head described as it rested on the pillow. None of these movements was a straight line, and this is not a lack of coordination. It is not muscle laziness or distraction. It is something much deeper. It is the universe behaving exactly the way it always has, since before anything existed that could observe this behavior. The straight line is a wonderful human idea. It is useful, it is efficient on paper, it works well on maps and in engineering blueprints. But in the real physical world, the straight line is a foreigner. It appears sometimes under very specific and controlled conditions, and even then, if you look closely enough, you will find imperfections, microscopic curvatures, tiny deviations that betray the truth. Nature did not forbid the straight line from existing, but it clearly never chose it as its preferred language. And the interesting thing is that you already knew this, not with words, not with concepts, but with your body. You have felt it when watching the smoke from a candle dissolve in the air, when seeing how water flows between stones, when noticing that no tree branch grows at a perfect, uninterrupted angle. There is a quiet voice inside us that recognizes the coiled, the wavy, the spiral as the native language of the world, and the straight line as a construction, as an effort, as an artifice. What this nighttime stroll will do is simply invite you to look more calmly at what you already know. There are no violent revelations here. There are no great scientific scares saved for the end. There are layers. Layers that open slowly, like flowers that bloomed before dawn and that you didn't see because you were sleeping. The first thing worth undoing is a myth that seems reasonable at first glance. Many people believe that nature chooses the shortest path, and that the shortest path between 2 points is always a straight line. This deep down is a geometric definition that Euclid formalized about 2,300 years ago in a sunny Alexandria. It was a geometry of the plane, a geometry imagined on perfectly flat surfaces, without mass, without gravity, without time. A geometry of blackboards. The problem is that the universe does not live on a blackboard. The universe lives within itself, and itself is curved. Not metaphorically curved, not approximately curved. Geometrically, mathematically, observationally curved. The space between you and the ceiling of your room is not flat in the same way that the space between you and the distant star is not flat. The difference is that on everyday scales the curvature is so small that we can ignore it without serious consequences, but it is there. It always has been. Albert Einstein, in a work that lasted approximately 10 years and ended in November 1915, managed to mathematically describe what this means. The general theory of relativity revealed that mass curves the space around it, and that this curvature is what we call gravity, not a mysterious force that pulls things, but a geometry that directs movement. A planet is not pulled toward the sun as if there were an invisible rubber band between them. The planet simply follows the most natural path available within a space that the sun's mass has bent around it, and this most natural path within a curved space has a beautiful technical name, geodesic. The geodesic is the relativistic equivalent of the straight line. It is the most efficient path, the route of least resistance, the trajectory that anything with no force acting upon it will naturally follow. But in a curved geometry, the geodesic is not straight. It obeys the curvature of space like a boat obeys the ocean currents, not because it is being pushed, but because that is the contour of the available reality. Imagine a surface like that of an orange. If you draw a straight line between 2 points on this surface, using its contour, you will describe an arc. Not because you are being lazy or imprecise, but because the available space is curved and the shortest possible line within that space is necessarily an arc. This is what mathematicians call non-Euclidean geometry, and it is what describes with impressive precision the behavior of the real space where we live. Now, you might say, alright, space is slightly curved because of gravity, but things in my daily life don't suffer this effect in a perceptible way. And you would be right for the most part. The curvature that the Earth imprints on the space around it is enough to keep the moon in orbit and make apples fall from trees, but it is not enough to twist a ruler or visually deform the path between you and the wall. For daily human experience, Euclid still works well. But the universe is not just your bedroom. And even in your bedroom, there are other reasons why the straight line fails before it even enters the scene. Reasons that have nothing to do with relativity or gravitational curvature. Reasons that live in the very structure of matter, in the behavior of forces, in the nature of growth and flow. Think of the water in a river. A river in its most natural state does not flow in a straight line. It flows in long, lazy curves that geographers call meanders. And there is an elegant reason for this, a reason that mixes physics, geometry, and something that almost seems like an aesthetic preference. When water flows, it does not encounter perfectly uniform terrain. There are small irregularities, slightly larger grains of sand, almost invisible stones, microscopic variations in soil density. Any small perturbation makes the water deviate slightly, and here something fascinating begins. Once there is a deviation, even if it is tiny, the very physics of the flow amplifies this deviation over time. The water flowing along the outer bank of a curve moves faster and erodes more. The water on the inner bank moves slower and deposits sediment. This deepens the curve. The deepened curve makes the flow deviate more. The larger deviation creates a more pronounced curve, and so the river coils upon itself in increasingly generous spirals, not despite physics, but because of it. The same principle appears in the wind that forms tornadoes, in the smoke that rises in spirals from a bonfire, in the pattern clouds formed over the ocean when photographed from space. There is a fluid dynamics that favors rotation, coiling, swirling, instead of straight, calm flow. When you mix two fluids of different densities, like hot and cold water, the result is never a uniform, direct mixture. It is a ballet of filaments that coil around each other in patterns that seem almost choreographed. The deepest reason behind this has to do with something called potential energy, and with a principle that can be formulated in different ways but appears throughout physics as a sort of fundamental law of cosmic laziness. Systems tend to evolve toward states of lower energy. And it turns out that in many situations, the state of lowest energy is not a straight state, but a curved, folded, coiled state. Think of a sheet of paper. If you hold it by both ends and let it hang, it will curve. Not because the sheet wants to bend or because there is some mysterious force pulling the middle of the sheet down, but because the curved configuration redistributes tensions in a way that the system accepts with less effort than the straight configuration. The straight line, in this case, would require you to apply active force to keep the sheet horizontal. The curve is what happens when you let physics work on its own. This is a pattern that will appear repeatedly throughout this night. The straight line requires effort, the curve is the path of least resistance. The straight line is what we build when we want to control. The curve is what we find when we observe. There is also something very interesting happening at the scale of atoms and molecules, something that begins to explain why not even the smallest constituents of matter organize themselves into perfectly straight structures. A chain of carbon atoms, which is the basis of all organic chemistry and therefore of all life on Earth, is not a stretched thread. It is a chain with specific angles between each bond determined by the geometry of the electron cloud around each atom. These angles are not chosen arbitrarily. They are determined by the principle of electrostatic repulsion between the pairs of electrons that form the bonds. Each pair of electrons repels the other pairs, and they arrange themselves in space so as to be as far apart from each other as possible. This arrangement of minimum repulsion, of balance between forces that push each other, rarely produces a straight line. It produces tetrahedrons, pyramids, angled structures that seemed arbitrary until we understood the electrical geometry that governs them. A water molecule, which is perhaps the most studied substance in the history of science, has the shape of an open V. Oxygen in the center, two hydrogens at the ends with an angle of 104.5 degrees between them. Why this specific angle and not a straight line of 180 degrees, which would be the simplest to imagine? Because oxygen has two pairs of electrons that do not participate in any bond called lone pairs, and these pairs push the bonds with the hydrogens into an angular position that minimizes total repulsion. The water molecule is angled not by accident but by geometric necessity, and this apparent peculiarity of such a small molecule has enormous consequences. The angulation of the water molecule creates an imbalance in the distribution of electrical charges within it, making it polar with a slightly positive side and a slightly negative side. This polarity is responsible for the surface tension that allows insects to walk on water, for water's ability to dissolve most substances, for the anomaly that makes ice less dense than liquid water and therefore float, which in turn was fundamental for the survival of life in cold climates throughout ice ages. All this because a molecule refused to be a straight line. There is a larger scale where the same refusal appears, with even more dramatic consequences. In the cosmos, the large structures of the universe, the galaxies, the galaxy clusters, the filaments of matter that connect these clusters like a cosmic spider web, none of this is straight. Spiral galaxies, which include our own Milky Way, have that swirling shape which is perhaps the most iconic image in all of astronomy. And the question of why galaxies are spiral and not flat disks or uniform spheres, or why not line-shaped clouds, is a question that leads directly to the heart of how matter organizes itself under the influence of gravity combined with motion. When a cloud of gas in space begins to collapse under its own gravity to form a galaxy, it is almost never perfectly still. There is always some residual rotation, some angular momentum accumulated over time. As the cloud shrinks, this rotation accelerates by the same principle that makes a skater spin faster when they pull their arms in. Angular momentum is conserved, and since the cloud is shrinking, the rotation speed increases. This increasing rotation throws matter outward in the equatorial plane of rotation, forming a disk. And the gravitational perturbations within this disk, density waves that propagate like waves in water, create the spirals. The spirals of galaxies are not rigid structures like the blades of a fan. They are patterns like standing waves, regions where matter compresses and disperses in regular sequence as the galaxy rotates. It is a dance of density, not a fixed structure. The Milky Way, where we live, has a diameter of approximately 100,000 light-years and a disk thickness of about 1,000 light-years in the plane. Our solar system is located about 26,000 light-years from the galactic center in a region of the Orion Arm, which is a minor spiral arm. It takes us about 225 million Earth years to complete an orbit around the center of the galaxy. In this time, called a galactic year or cosmic year, the Earth has already passed through ice ages, the emergence of dinosaurs, mass extinctions, and the appearance of the first mammals. And our trajectory around the galactic center is not a perfect circle nor a straight line. It is a slightly perturbed ellipse, influenced by the gravity of the spiral arms, by the star clusters we cross along the journey, by the distribution of dark matter that permeates the galaxy like an invisible skeleton. Dark matter is one of the great characters in this story, even though we still don't understand what it really is. We know it exists because the gravitational effects we observe in galaxies cannot be explained by visible matter alone. The stars at the outer edges of spiral galaxies move too fast to remain in orbit if there were only the matter we can see. There is something else there, something that does not emit or reflect light, but has mass and therefore curves space and influences the movement of everything around it. About 27% of the energy content of the universe is dark matter. About 68% is dark energy, a form of energy that permeates empty space and is making the universe expand faster and faster. Only about 5% is ordinary matter, the matter made of atoms, the matter of which you, your pillow, and the stars you can see in the sky are made. We are the exotic minority in a universe dominated by things we still don't know how to name properly, and this mystery-dominated universe expands. It does not expand into a larger space that already existed before. It expands within itself, creating new space between all gravitationally bound structures. Galaxies do not move away from each other like fragments of an explosion spreading through the void. The space between them grows like dots marked on an inflating balloon. The movement of distant galaxies moving apart is not movement through space. It is space growing between them. And this growth of the universe, this cosmic expansion that began with the Big Bang approximately 13.8 billion years ago, is also not uniform, not linear, not straight. The distribution of matter in the primordial universe had small density fluctuations, microscopically denser regions and microscopically sparser regions. Over billions of years, gravity amplified these differences, pulling more matter into the already slightly denser regions and emptying the already slightly sparser regions. The result is the large-scale structure of the universe we observe today. Filaments of galaxies separating immense voids like bubbles of cosmic foam, a web that stretches across the entire observable extent of the cosmos. This web has no straight lines. It has curves, knots, sinuous filaments, regions of density that fold around absences. It is the most grandiose structure that exists, and it is as intrinsically curved and irregular as a river in a valley or a water molecule. But let's return for a moment to something closer, more tangible, more intimate, to your own body. You are lying down now and there is a spine inside you. This spine is not straight. It has double S curvatures. When viewed from the side, the cervical lordosis in the neck, the thoracic kyphosis in the middle of the back, the lumbar lordosis in the lower back. These curves are not deformities, they are adaptations. A perfectly straight spine would be catastrophically fragile under impact, like a rigid rod. The curves distribute compression forces, absorb the impact of each step, allow the flexibility needed to bend, twist, and balance the weight of the head on a moving body. Your long bones, the femur, the humerus, the tibia, are also not perfectly straight. They have a subtle curvature that distributes mechanical stress along their length. Your lungs are not rectangular sacs but tree-like branched structures, with the trachea dividing into bronchi, which divide into bronchioles, which end in alveoli, tiny air sacs where oxygen enters the bloodstream. The branching pattern is fractal, each division similar to the larger division that preceded it, creating an immensely large gas exchange surface within a relatively small volume. It is a geometric trick that nature repeats exhaustively because it works. Your arteries and veins are not straight tubes that carry blood from A to B by the most direct route. They are networks that branch, curve, and adapt to the available space between other organs and structures. Capillaries form networks so dense and intricate that every cell in your body is at most a few tenths of micrometers away from a blood vessel. This network is only possible because it completely abandons any idea of a straight trajectory in favor of a complex three-dimensional geometry that maximizes coverage and minimizes average distance. The neurons in your brain, which at this moment are gradually slowing down their activity as sleep approaches, have a tree-like shape. The cell body in the center, the dendrites branching like twigs to receive signals, the axon extending like a trunk and then branching into terminals that connect with other neurons. There is no straight line in this architecture. There is a geometry of connection that seems disordered at first glance but is actually the most efficient way to distribute connectivity within a limited volume. The human brain has about 86 billion neurons. Each neuron makes an average of 7,000 connections with other neurons. The total number of connections in the brain is of such an order that it far exceeds the number of stars in the Milky Way. This entire network of connections, this cosmos compressed within your skull, is made entirely of curves, trees, networks, spirals, structures that the universe clearly prefers over the straight lines that human thought sometimes idealizes. And there is something profoundly beautiful about this, something worth letting rest softly as your eyes grow heavy. The curved universe is not a defective universe. It is a universe that has found over billions of years the shapes that work. Curves survive because they distribute, because they adapt, because they absorb, because they connect in ways that straight lines simply cannot. Curvature is not the absence of order, it is a more sophisticated form of order, an order that emerges from the forces and constraints of the real physical world. And when you watch the smoke from that imaginary candle dissolving in the air, when you follow with your eyes the sinuous line of a river on a map, when you feel your spine resting in the curve of the mattress, you are in touch with this ancient principle, older than the earth, older than the stars that formed the atoms of your body, as old as the first density perturbations in the primordial universe that would be amplified over billions of years into spiral galaxies and cosmic filaments and angled molecules and meandering rivers and branching neurons that now gently slow down as sleep arrives. One question remains that we haven't touched yet, that still floats over all this like mist. If the universe has such a preference for curves, if forces and geometries and fluid dynamics and quantum physics and general relativity all conspire to produce curves instead of straight lines, where does the energy that animates this entire system come from? What primordial force continues to push rivers to meander, galaxies to spin, atoms to angle, neurons to fire? What sustains the dance? The mist that floats over this question has a specific scent. It is the scent of something that has always been there, so present that it becomes invisible. When you heat a pot of water and watch the first bubbles form at the bottom, rising in irregular spirals to the surface, you are watching the most everyday demonstration of a principle that governs everything from the ignition of the first stars to the gentlest meander of a river in the Amazon. What moves those bubbles is not simply heat, it is the difference between hot and cold. It is the gradient. It is the imbalance itself that becomes the driving force. Think of what it's like to enter a room where the temperature is perfectly uniform, where every corner has exactly the same warmth, where there is no colder wall or hotter window. Nothing moves in this room. The air stays still. Dust does not circulate. There is no breeze, no convection, no life in the dynamic sense of the word. This theoretically perfect room, this environment of absolute equilibrium, is the closest state to death that physics knows. Physicists have a name for this final state, this ultimate destiny of everything that exists, where all gradients dissipate and nothing can move anything anymore. They call it the heat death of the universe. And the fact that we haven't reached it yet, the fact that the universe still boils with activity and curves and spiral movements, means that we still have energy available to spend, we still have imbalances to resolve. The source of all this curvature, of all this refusal of the universe to accept straight lines, is fundamentally this. The universe was born in a state of extraordinary imbalance, and all the curved shapes we see around us are the physical signature of systems trying to resolve this imbalance over time. The river does not meander because it decided to be artistic. The river meanders because it is solving an energy gradient problem in the most efficient way possible for the conditions it finds itself in. The galaxy does not spin in a spiral for aesthetics. It spins in a spiral because angular momentum and gravity and mass distribution create a system of imbalances that can only be resolved through that specific shape. There is a man who spent decades trying to understand why rivers do exactly what they do, and his story is one of the most beautiful examples of how science sometimes needs to slow down to see what is right in front of it. Harald Elfen, a Swedish physicist who received the Nobel Prize at the end of the last century, dedicated part of his work to understanding how conductive fluids behave in the presence of magnetic fields. He discovered that plasma, this state of matter that makes up stars and most of the visible universe, does not move in straight lines because magnetic field, lines and plasma flow coil around each other in extraordinarily complex ways, creating structures we now call flux tubes and plasma filaments, all curved, all spiral, all obeying the same fundamental logic that a perturbed system finds equilibrium through curvature and not through straightness. But before Alphen, even before we had the language to talk about plasma and magnetic fields, there was a man sitting on the banks of the Arno in Florence, filling notebooks with observations about water. Leonardo da Vinci, in the late 15th and early 16th centuries, dedicated hundreds of pages to the behavior of fluids. His notebooks show vortices drawn with a precision that anticipates by 4 centuries what modern physics would call turbulence. He observed how water around an obstacle does not simply deflect and continue in a straight line on the other side. It spins, it forms spirals that persist far beyond the obstacle. It carries the memory of the encounter with that stone or that curve of the riverbank, and this memory is expressed in the form of rotation, in the form of curvature that lasts and lasts until it is finally dissipated by friction. Leonardo didn't have the equations. He didn't have the mathematical vocabulary. But he had something that mathematicians sometimes lose, the patience to observe without trying to simplify. He let the phenomenon be complex, and what he saw repeatedly was that nature solves flow problems through curves, never through straight lines. The physical law at the heart of all this has a name that seems too simple for the weight it carries. The second law of thermodynamics. It says, in its most stripped-down form, that isolated systems tend to go from states of lower probability to states of higher probability, that spontaneous order unravels, that heat flows from hot to cold and not the other way around. But there is a consequence of this law that is often neglected in standard didactic presentations. While a system is in the process of moving from imbalance to equilibrium, while it still has gradients to resolve, this resolution process is extraordinarily creative. It produces structures, it produces patterns, it produces curves. The physicist Ilya Prigogine, Belgian of Russian origin, received the Nobel Prize in Chemistry in the late 70s for realizing exactly this. He studied systems that were far from thermodynamic equilibrium, systems through which energy flowed continuously, and discovered that these systems, instead of simply dissipating chaotically, sometimes self-organized into coherent structures. He called these structures dissipative structures because they exist precisely while they are dissipating energy, precisely while they are resolving a gradient. When the dissipation ends, when the gradient is exhausted, the structure disappears. A candle flame is a dissipative structure. It has a recognizable shape, a stable geometry, a tip that curves slightly in the direction of the air convection around it. But this shape only exists because there is wax melting, fuel being consumed, an energy gradient being resolved in real time. Blow out the candle, eliminate the gradient, and the structure is gone immediately. The universe, in this perspective, is replete with dissipative structures on all scales. Rivers are dissipative structures. Hurricanes are dissipative structures. Living cells are dissipative structures. And all of them, without exception, have curved shapes. There is a reason for this that goes deeper than any specific law, and it has to do with something called the principle of minimum entropy production. When a system far from equilibrium finds a steady state, that steady state tends to be the one that produces the minimum entropy compatible with the system's constraints. In simpler terms, nature tends to find the most efficient way to dissipate the available gradient, and this most efficient way is almost never a straight line. To understand why, consider two paths between two cities. One path is a straight line that crosses a mountain. The other is a road that goes around the mountain in gentle curves. The straight line seems shorter on the map, but the energy expenditure to travel it is much greater. Water, unlike humans, with their motorized vehicles, does not have the option of insisting on the straight line by paying an extra energy cost. It simply flows where energy takes it with the least resistance. And this path of least resistance, when the terrain has any kind of variation, any perturbation, any roughness, is almost always a curve. There is another fundamental law at play here, and it is even older in the history of physics, although its complete formulation took centuries to mature. The law of conservation of angular momentum says that a rotating object resists changes to its rotation unless an external force acts upon it. It seems like a dry technical statement until you think about what it means in practice. When an interstellar gas cloud begins to collapse under its own gravity to form a star, any minimal rotation that cloud had, any tiny perturbation that made it spin imperceptibly, is amplified as the cloud contracts. It is the same principle that makes a skater spin faster when they pull their arms close to their body. The material forming the star and the protoplanetary disk around it cannot simply fall in a straight line to the center because angular momentum must be conserved. It has to go somewhere. And the place it goes is rotation, the spiral, the curvature. The first person to clearly formulate the law of conservation of angular momentum was the astronomer Johannes Kepler, although he did not use this modern terminology. Kepler, studying the orbits of planets in the early 17th century, noticed that planets did not move at a constant speed along their elliptical orbits. They accelerated when they were closer to the Sun and decelerated when they were further away, and the area swept by the imaginary line between the planet and the Sun was the same for any equal period of time, regardless of where the planet was in its orbit. He called this his second law. What this law described, without Kepler knowing it at the time, was the conservation of angular momentum, and it was the reason why orbits were ellipses and not perfect circles, curves instead of ideal shapes, expressions of real physics and not abstract geometry. Newton, decades later, showed that Kepler's laws could be mathematically derived from a more fundamental law of gravitation. But what Newton did was, in a sense, steal a bit of the magic of the moment. Kepler's ellipses were astonishing precisely because they were raw data, pure observations, patterns found in the sky without a prior mechanism to explain them. The universe curved the orbits of the planets and Kepler simply saw. Before understanding why, this story matters because it repeats throughout the entire history of science related to curves. Someone observes a curved pattern, gets intrigued, tries to simplify it, realizes they cannot, and then finally discovers that the curvature was not a deviation from the true pattern, but was the true pattern, the most direct expression of nature's deepest laws. Daniele Bernoulli, in the 18th century, was studying the behavior of fluids in tubes of different diameters. He discovered something that seemed counterintuitive. Where the fluid moved faster, the pressure was lower. Where it moved slower, the pressure was higher. This became known as Bernoulli's principle, and it explains everything from how airplane wings generate lift to why rivers, when encountering a narrowing in their bed, accelerate and then open up again when the bed widens. But what Bernoulli's principle also explains more subtly is why rotating fluids tend to organize into coherent structures. The pressure difference between the inside and outside of a vortex is what keeps the vortex cohesive. It is what makes a tornado maintain its shape as it moves across the landscape. It is what makes a hurricane have that calm eye in the center surrounded by walls of spiraling clouds. The fundamental imbalance that makes all this work can be expressed in a very simple way, almost disturbingly simple for something that explains so much. Two points with different energies, separated by a path through which something can flow. That's all. 2 points in imbalance and a means of communication between them. The hot sun and cold space, with planets and atmosphere and oceans in between. The high mountain and the low valley, with the river in between. The hot core of the earth and the cold surface, with the mantle of partially molten rock, in between convecting in giant cells. The concentration gradient of ions inside and outside a nerve cell, with the cell membrane in between regulating the flow. In all these cases, what we observe is that the process of resolving the imbalance, the flow of energy or matter from the higher to the lower energy state, does not happen in a straight line. It happens through structures, through patterns, through curves that maximize the efficiency of the process, that distribute the flow so that a highly complex system can maintain coherence while dissipating the energy that keeps it alive. There is an experiment that can be done in any kitchen that demonstrates this in an almost hypnotic way. Heat a shallow layer of oil in a dark-bottomed pan as evenly as possible, and then let it cool slightly, and sprinkle a little powder on the surface to make the patterns visible. When the oil is being heated from below and cooled from above, something happens that Henri Bénard first observed in 1900. The fluid self-organizes into hexagonal convection cells. The hot material from the bottom rises through the center of each cell, moves horizontally on the surface, cools and then descends along the edges of the cell to restart the cycle. These Benar cells, as they became known, are perfect dissipative structures. They exist precisely because a temperature gradient is being maintained, and the patterns they form are not random. They are the most efficient patterns possible for transferring heat from the hot bottom to the cold top, given the specific conditions of viscosity and conductivity of the fluid. Lord Rayleigh, the British physicist who mathematized Benard's work in the early 20th century, showed that these cells only appear when the temperature gradient exceeds a certain threshold, a dimensionless number that today bears the name of both, the Rayleigh-Benard number. Below this threshold, heat propagates simply by conduction, crossing the fluid without moving the fluid itself. Above the threshold, the fluid can no longer stand still. It begins to move, and when it begins to move, it moves in curves. This moment of transition, this crossing of a threshold beyond which the system chooses movement over stasis, is one of the most universal patterns in nature. It appears in fluid physics as the Rayleigh-Benard instability. It appears in chemistry as the Belousov-Jabotinsky reactions, where chemical reagents alternating between oxidation and reduction states produce visible spiral waves that propagate across a petri dish like miniature galaxies. It appears in biology as developmental patterns, where embryonic cells, receiving gradients of signaling molecules, differentiate into different tissues following rules that produce shapes that are always curved, always organic, never angular in the purely geometric sense. Boris Belousov was a Russian chemist who in the 50s discovered a chemical reaction that seemed to violate the second law of thermodynamics, at least at first glance. The mixture of reagents he prepared did not simply reach equilibrium all at once, it oscillated. It turned red, then blue, then red again in regular cycles that could last for hours. His attempts to publish the result were repeatedly rejected by reviewers who simply did not believe such a thing was possible. It took over a decade for Anatol Jabotinsky to resume the work, perfect it, and demonstrate that there was no violation of the second law. The reaction was indeed moving towards equilibrium, but it was doing so in a spiral instead of a straight line, oscillating around the equilibrium state instead of converging directly to it. This is the pattern nature prefers when it has a choice, when the gradients are strong enough and the conditions are complex enough. Not the straight line towards equilibrium, the spiral around equilibrium, the meander towards the destination, the vortex that spins as it falls. The question of where the energy that animates the entire system comes from has an answer that is simultaneously very specific and very broad. Very specific because we can point to it, the nuclear energy in the core of the sun, converted into photons of light that travel 8 minutes and a few dozen seconds to reach Earth, heating the surface unevenly, creating temperature gradients that move the atmosphere, that move the ocean water, that feed the hydrological cycle, that gives energy to rivers, that transports sediment, that sculpts the riverbed, that determines where the river will curve in the next rainy season. This is the specific causal chain. But the answer is also very broad because there is nuclear energy in the sun thanks to an older imbalance, the collapse of an interstellar gas cloud under gravity about 4.6 billion years ago. And this collapse was possible thanks to density perturbations in the primordial universe, and these perturbations were possible thanks to quantum fluctuations in the fraction of a second after the Big Bang, when the universe was still smaller than a grain of sand and already in that infinitesimally small moment. Curvature over straightness. There is a word physicists use to describe the type of system that maintains its structure while receiving a continuous flow of energy from the outside. Open system far from equilibrium. A river is an open system far from equilibrium. It receives water from rain, gravitational energy from altitude, sediment from slopes, and processes all this through its curves, its rapids, its meanders, exporting slower water and deposited sediment and dissipated heat to the ocean and the atmosphere. The cycle restarts when the sun heats the ocean and evaporates more water that rises, condenses, and falls again on the mountains. Every meander a river forms is a local solution to a specific flow problem. The water encounters a minimal perturbation in the bed, a slightly protruding rock, a variation in the hardness of the substrate, and begins to curve. This curvature creates a velocity difference between the inner bank and the outer bank of the curve, the outer bank moving faster and eroding more, the inner bank moving slower and depositing more sediment. The curve sharpens, the curve deepens, and then the river has an established meander where before there was an almost straight line. This happens at one point in the river, in one curve, in one rainy season. What happens when this process repeats not once, not 100 times, but thousands and millions of times in different rivers, on different scales, over periods measured not in years, but in entire geological eras? When a single meander establishes itself in a stretch of river, it does not remain alone for long. The curvature that has just been born alters the pressure field of the water that comes after. The flow reaches the next section with a hydrodynamic memory of the previous curve, with a rotational tendency already inscribed in its velocity. And this makes the probability of a second curve forming enormously higher than it would be in a virgin, indifferent stretch. The river plans nothing. The river has no intention. But the river learns in a way that is not learning in the conscious sense of the word, but which has all the practical effects of deep, irreversible learning. This chaining of curves creates something that geomorphologists call the meander wavelength. There is a surprisingly constant proportion between the width of a river channel and the average distance between the crests of its meanders. Very different rivers on different continents, in different climates, with completely different water discharges, tend to obey this proportion with a regularity that defies the intuitive expectation that each river would be a particular unique case. The proportion is not identical in all cases, but the tendency to maintain a stable geometric relationship between width and meander wavelength is universal enough to have been described mathematically in the last century, and to continue to be studied as one of the most elegant examples of self-organization in flow systems. The geomorphologist Luna Leopold, working in the United States in the second half of the 20th century, dedicated decades to trying to understand why rivers of such different sizes converge towards meandering geometries so similar in proportional terms. Leopold and his collaborator M. Gordon Wollman collected data from rivers all over the world, measured widths, wavelengths, meander amplitudes, and found patterns suggesting that meandering was not a local topographic accident, but an almost inevitable consequence of the laws governing the transport of sediment-laden fluids. There was order there was repetition, and this repetition had not been planned by any external agent, but had emerged from the interaction between moving water, gravity, friction, and the tendency of physical systems to dissipate energy in particular ways. The idea of energy dissipation is central to understanding why patterns organize the way they do. A straight river, in theory, would transport water from one point to another with maximum efficiency, with the shortest possible distance between source and mouth. But maximum transport efficiency also means that the fluid arrives at its destination with kinetic energy that needs to go somewhere, and this energy needs to be absorbed by the substrate, eroding the banks intensely and concentratedly. Meandering, paradoxically, is a way for the river to distribute the work of dissipating energy over a longer course, slowing the flow, creating alternating zones of deposition and erosion, and reaching the mouth with a more balanced energy more compatible with the substrate's resistance. The curved river is longer, but it is also more sustainable from an energetic point of view. The curve is not inefficiency. The curve is a compromise solution between multiple simultaneous physical demands. And when this compromise solution repeats over hundreds of kilometers of river course, the visible result from space is one of those structures that seem deliberately drawn but were drawn by no one. Aerial photographs of large alluvial plains show rivers folding over themselves in patterns so regular that the first reaction of an observer unfamiliar with geomorphology is to ask who built them that way. The answer is that they built themselves through the accumulation of countless local adjustments that converged into a coherent global shape without any of the system's components being aware of the global shape being produced. The same principle that governs a river on one continent governs rivers on other continents, but it also begins to govern other scales and other types of flow. Ocean currents, which are essentially rivers of hot or cold water moving within a much larger ocean, also meander. The Gulf Stream, carrying warm water from the tropical Atlantic towards the North Atlantic, does not travel in a straight line from one side to the other. It oscillates, it curves. And these curves, just like the meanders of a fluvial river, are not random. They have characteristic wavelengths. They have amplitudes that vary within certain limits. They have a geometry that reflects the balance between the energy of the flow, the friction with adjacent water masses, and the influence of a factor that in the oceans has a much greater weight than in continental rivers. This factor is the rotation of the Earth. The planet spins on its own axis, and this rotation creates an effect that physicists call the Coriolis force, which is not exactly a force in the Newtonian sense, but an apparent effect that any moving object experiences in a rotating reference frame. In the oceans and the atmosphere, scales where moving fluids travel distances large enough for the curvature of the Earth's surface and its rotation to be relevant, the Coriolis force acts by deflecting fluids to the right in the northern hemisphere and to the left in the southern hemisphere. This systematic deflection, combined with the differences in temperature and salinity that create density gradients in the oceans, produces circulation patterns that have a global asymmetry inscribed in the very structure of the planet. The great ocean gyres, the basin-scale circulations that redistribute heat between the tropics and the poles, have a geometry that reflects this fundamental asymmetry. In the North Atlantic, the current flows north along the east coast of North America with more intensity and speed than it flows south along the European coast. This phenomenon, known as western boundary intensification, is a direct consequence of how the Coriolis force interacts with the vorticity imposed by the wind and the geometry of the ocean basins. Benjamin Franklin, who was much more than the inventor popular history tends to remember, was one of the first to map the Gulf Stream with some rigor, noting that ships following the correct route arrived faster from Europe to the American colonies than those trying to go against the current or those who simply had no knowledge of its existence. He did not have the mathematical language of the Coriolis force, which would only be formalized decades later, but he had the empirical observation that the ocean had structure, had patterns, had geometry. The geometry of the ocean on a large scale is not just the geometry of surface currents. It is also the geometry of internal waves, the oscillations that happen within the water column at interfaces between layers of different densities, invisible on the surface but with amplitudes that can be much larger than those of surface waves, and with periods measured in hours or days instead of seconds. It is the geometry of ocean fronts, where water masses of different temperatures meet and create edges that, seen from satellite, have the fractal complexity of a continental coast with recesses and protrusions that repeat at multiple scales. It is the geometry of mesoscale eddies, swirls of warm or cold water with diameters of tens to a few hundred kilometers that separate from the main currents and drift slowly across the ocean for months. carrying their temperature and salinity characteristics and the biological communities that inhabit them as if they were mobile islands in a liquid plain. These ocean eddies, when viewed together on a long-term map, are not randomly distributed across the oceans. They appear in preferential regions, form populations with defined statistical characteristics, move in directions that reflect environmental vorticity gradients. Where a distracted observer would see only chaos, an oceanographer with access to long-term data sees a statistical order that is not immediately visible but governs the system's dynamics with an influence that accumulates over time. The atmosphere, thinner and faster than the ocean but governed by the same fundamental principles of fluid dynamics and the same planetary rotation, produces its own large-scale patterns. The Hadley cells, which organize tropical circulation into two symmetrical rings relative to the equator, with warm air rising in the tropics and descending in the subtropics, are a direct consequence of the balance between the differential heating of the Earth's surface and the tendency of the atmospheric fluid to equalize pressures and temperatures. But the Hadley cells do not exist in isolation. They interact with the Ferrel cells in the mid-latitudes and with the polar cells in the high latitudes, creating a general atmospheric circulation that has been described and mathematically modeled with increasing precision since the pioneering work of George Hadley in the 18th century and the subsequent contributions of William Ferrel in the 19th century. Ferrel was a relatively obscure American meteorologist during his lifetime, working in his spare time while teaching in rural schools, who managed to infer the existence of the circulation that today bears his name from theoretical principles and available observations long before having access to any systematic global data. There was an asymmetry in the winds of the mid-latitudes that empirical observations by navigators had known for centuries, the westerly winds that dominate temperate latitudes, but no one had managed to explain this asymmetry within a coherent theoretical framework that connected it with global circulation. Ferrel did this, and in doing so took one of the first steps towards understanding the atmosphere not as a collection of separate local phenomena, but as a global system with a coherent geometry that extends from pole to pole. This global geometry of the atmosphere includes the jets, high-speed air currents that circulate at high altitudes and have an enormous influence on the climate of the regions they overfly. The polar jets in particular do not follow a straight path around the poles. They wave. They meander in structures that meteorologists call Rossby waves, named after the Swedish-American oceanographer Carl Gustav Rossby, who described them mathematically in the first half of the 20th century. Rossby waves are large-scale oscillations in the atmospheric wind field that emerge from the interaction between the zonal flow and the latitudinal gradient of the Coriolis force, which is greater at the poles than at the equator because the vertical component of the Earth's angular velocity varies with the cosine of latitude. Rossby discovered that these waves had very particular properties, unlike waves in the sea, which propagate their energy in the same direction they move. Rossby waves propagate their energy westward, while the physical structures visible in the wind field often move eastward with the background flow. This asymmetry between the phase velocity and the group velocity of the waves, between the speed at which the peaks and troughs of the wave move and the speed at which the energy propagates, is one of the most counterintuitive aspects of atmospheric dynamics and one of the most important for understanding how local perturbations in the atmosphere can have effects at great distances and after long intervals of time. When the polar jet meanders with very large amplitude, the peaks of the Rossby waves can extend deep south, bringing Arctic air to temperate latitudes, and the troughs can extend north, bringing tropical air to subpolar latitudes. These extreme meandering events, known as blocking in English, and which do not have an established, universally accepted translation in Portuguese, are responsible for some of the most disruptive, extreme weather events in the mid-latitudes: prolonged heat waves, cold snaps that persist for weeks, droughts that last for months. The meandering of the jet is not just a geometric detail of how the atmosphere organizes its winds. It is a fundamental mechanism for redistributing thermal energy between latitudes, and its fluctuations have consequences that affect hundreds of millions of people. The timescale on which the polar jet meanders is days to weeks. The timescale on which ocean meanders evolve is months to years. The timescale on which fluvial meanders transform is decades to millennia. But on all these scales, the fundamental process is the same. A moving fluid in a gravitational field on a rotating planet tends to develop instabilities that take it away from the straight path, and these instabilities organize into patterns with characteristic geometries that are different in detail but similar in principle. Curvature is not an exception. Curvature is the rule repeated on scale after scale, in fluid after fluid, on planet after planet, because the laws that govern it are not specific to Earth but are consequences of the fundamental physics of motion. The patterns that emerge from this repetition on multiple scales have a property that mathematicians and physicists have identified and studied with growing enthusiasm since the second half of the 20th century. They exhibit self-similarity. A continental coast, with its recesses and protrusions that repeat on scales ranging from kilometers to hundreds of kilometers, has a complexity that Benoit Mandelbrot, the Franco-American mathematician who formalized fractal geometry, used as one of the central examples of his revolutionary work. Mandelbrot asked, in a question that seemed simple but contained a disturbing depth, what the length of the coast of Great Britain was, and he showed that the answer depended on the scale with which you measured. The finer the ruler, the more details of the coast you captured, the more curves and recesses you included in the measurement, and the greater the length you obtained. A coast does not have a fixed length. A coast has a fractal geometry, a geometry whose perimeter diverges as the measurement scale decreases. This fractal property of coastlines, which Mandelbrot was describing in abstract mathematical terms in the 70s, is the direct result of the physical processes that shaped these coasts over geological eras. Wave erosion, differential weathering of rocks with different hardness, sediment deposition in estuaries, the action of storm corridors that sculpt coasts in patterns that depend on the climatic history of each region. All these processes operate on multiple scales simultaneously and produce structures that have complexity on all these scales at the same time. The curvature of coasts, like the curvature of rivers and the curvature of ocean currents, is an emergent pattern, a consequence of physics operating in parallel on many scales, without supervisor, without plan, without architect. The distribution patterns of the planet's large geological structures have an order on an even larger scale. Mountain ranges are not randomly distributed across the Earth's surface. They concentrate along the margins of tectonic plates, where compression between convergent plates pushes the crust upwards, or where pressure relief in subduction zones generates volcanic chains. Oceanic rifts, where new plates form from magma emerging from the mantle, have a geometry that reflects both the internal dynamics of the mantle and the distribution of stresses in the lithosphere. Chains of volcanoes in the middle of the oceans, like Hawaii, form lines that trace the movement of plates over fixed hotspots in the mantle, punctuating with precision the kinematic history of the plate for tens of millions of years. This tectonic order, which organizes the largest structures on the Earth's surface into patterns that reflect internal dynamics, creates the topographic context within which all other patterns develop. Rivers meander on plains, but the destiny of the plains, their altitude, their slope, the thickness of the sediments that compose them, is determined by the tectonic history of the continent. Ocean currents circulate within ocean basins, but the geometry of these basins, the position of the continents that delimit them, is determined by the movement of plates over hundreds of millions of years. The meandering we see today in rivers and oceans and the atmosphere happens within a container whose shape was sculpted by even slower, even deeper processes. What emerges from all this multi-scale organization is an image of the planet not as a collection of separate, independent phenomena, but as a system of systems, where each level of organization is shaped by the larger levels that contain it and at the same time influences the smaller levels it contains. The meanders of the polar jet affect the climate of the regions they overfly, and this climate affects the erosion of landscapes, and this erosion determines the sediment load of rivers, and this sediment load influences the geometry of fluvial meanders. The cycle has no identifiable beginning or end. It is a web of feedbacks that spans timescales from hours to geological eras and spatial scales from millimeters to tens of thousands of kilometers. The dissonant beauty of this organization lies precisely in its lack of declared purpose. None of these large-scale curves and ripples and meanderings were designed. None of them has a creator in the usual sense of the word. Each of them emerged from the repeated, patient application of simple physical laws to initial conditions that varied slightly from place to place and from moment to moment. And this repetition accumulated over scales of time and space that surpass the intuitive capacity of the human mind to visualize, produced the complex, beautiful order we see when we look at the planet from space or study its patterns with the instruments of modern science. But there is an ingredient that complicates this picture, that makes it at the same time richer and more unpredictable, that takes the patterns we described and amplifies them, distorts them, branches them in ways that fluid physics alone would not produce with such exuberance. Without this ingredient, the patterns would exist, but they would be simpler, more regular, more easily captured by equations. The presence of this ingredient does not create curvature, but it transforms curvature into something that propagates and multiplies and becomes, under certain conditions, radically different from what the simplest models predict. This ingredient is life. Not life as a metaphor, not life as a philosophical concept applied to rocks and clouds, but life in the most literal and biological sense of the term. Organisms that breathe, that grow, that die, that reproduce, and in doing so, chemically, physically, and structurally alter every surface they touch. Life is the amplifier that Part 3 left suspended in the air as a promise, and it is powerful precisely because it seems, at first glance, incapable of competing with the forces that shape the planet. A plant seems fragile before a storm. A fungus seems invisible before a mountain range. A field of algae seems irrelevant before an ocean. But this intuition is completely wrong, and recognizing the error transforms the way one sees any landscape. Life does not fight fluid physics, it uses it. It inserts itself into existing patterns, into gradients of temperature and humidity and nutrients, and modifies them from the inside out, from the microscopic scale to the continental scale. It is an amplifier because it transforms weak signals into strong signals. A slightly more humid soil on a slope produces a plant. This plant produces shade, which keeps the soil more humid. This more humid soil produces more plants. This group of plants produces a microforest. This microforest alters the runoff pattern of rains. This runoff pattern forms a stream. This stream carves a valley. This valley channels winds. These winds bring seeds from other species. And this entire process, initiated by an extra grain of moisture on a slope, unfolds over millennia into something that occupies hundreds of square kilometers and which, seen from space, is unmistakable and completely different from the surrounding territory. The central mechanism behind this amplification has a name in science: positive feedback. It is a process in which the output of a system becomes the input of the same system, not to stabilize it, but to intensify it. Positive feedback is the opposite of equilibrium. It is the tendency that certain systems have, once perturbed in some direction, to continue moving in that direction with increasing speed. It is the mechanism by which small differences turn into large differences. And life is a very special machine for creating positive feedbacks in the environments it occupies. Consider what happens when the roots of a tree penetrate a crack in a rock. The crack was already there, produced by cycles of thermal expansion and contraction over perhaps thousands of years. The root did not create the crack. It simply found it and decided to use it. But by growing inside the crack, by expanding with each rainy season, by injecting organic acids that dissolve the rock's minerals, the root transforms a passive crack into an active site of disintegration. The rock was not simply eroded by water or wind. It was disintegrated by something alive that grew from the inside out. And when the rock finally breaks apart, the released soil feeds more plants, which penetrate more rocks, which release more soil. The process amplifies. This process has a technical name that rarely appears in everyday conversations, but describes something that is literally happening right now beneath the feet of anyone walking on land: biological weathering. The term comes from the English weathering, which in geology means the decomposition of rocks by the action of external elements. Weathering can be physical, when water freezes and expands in fissures, or chemical, when slightly acidic rain dissolves certain minerals. But biological weathering is the kind produced directly by living organisms, and it is in many landscapes the most powerful of the three. Lichens, which are organisms composed of fungi and algae living in symbiosis, were the first colonizers of bare rocks in the geological past and continue to be today. They secrete organic acids that dissolve the rock surface millimeter by millimeter over decades. When lichens die, they deposit organic matter that attracts bacteria and fungi. When these organisms accumulate in sufficient quantity, they create conditions for plants with larger roots to establish themselves. And so begins a process that can transform a completely bare rocky surface into fertile soil in a time frame measured in centuries. But life doesn't just amplify the physical landscape, it amplifies the local climate itself with an efficiency that took decades for scientists to begin to quantify properly. A forest is not just a collection of trees growing in a place where the climate is suitable. A forest is a system that actively creates its own climate, and this created climate feeds the forest, which amplifies the climate, which feeds the forest. Evapotranspiration, which is the process by which plants release water vapor into the atmosphere through their leaves, is responsible for an extraordinary fraction of the hydrological cycle in densely vegetated regions. In the Amazon, it is estimated that somewhere between 40 and 50% of all the rain that falls in the basin is water that was previously evapotranspired by the forest's own trees. The forest rains on itself. It is simultaneously the producer and consumer of its own moisture, and this closed cycle is one of the most impressive examples of positive feedback that exist on a continental scale. And here form enters the scene in the most direct way, because the forest is not flat. It is not uniform. It has canopy and subcanopy and understory and leaf litter, and each layer creates different conditions of light, temperature, humidity, and wind. And these different conditions select different species, which have different shapes, which create shadows in different ways, which produce leaves of different sizes, which fall at different times, which decompose at different speeds. The result is not a homogeneous carpet of vegetation, but a mosaic of textures and densities and ages and compositions. And this mosaic seen from space has a completely different appearance than any simple model of plant growth would produce. It is irregular in a specific way. It is complex in a non-random way. It is, like the sand ripples on the river bottom, fractal. The word fractal deserves to be pronounced carefully here because it carries a historical weight that enriches the conversation. The concept was developed by the mathematician Benoit Mandelbrot, who was born in Poland in 1924, grew up in France, studied in Paris, and spent much of his professional life in the United States, first at IBM and later at Yale. Mandelbrot was a man who didn't fit into the disciplinary boxes of the mathematics of his time. He was interested in irregularities, in shapes that traditional mathematicians considered aberrations or unimportant curiosities. He was interested in financial series that exhibited fluctuations that no model of the time could capture. He was interested in the distribution of errors in telephone transmission lines. He was interested famously in the length of the coast of Great Britain. The question about the length of the coastline seems trivial. It is the kind of question anyone would expect to see answered in some geography atlas. But Mandelbrot realized, based on earlier work by the British geographer Lewis Fry Richardson, that the answer depended radically on the scale of measurement used. If you measure the coast with an instrument that has a resolution of 100 kilometers, you get a value. If you measure with a resolution of 10 kilometers, you find all the bays and promontories that the previous measurement simplified, and you get a larger value. If you measure with a meter, you find every stone and every curve of every sand, and the length grows even more. And if you could measure with the resolution of a grain of sand, you would find even more irregularities, and the length would grow even more. In theory, an irregular coast has no finite length. If you keep increasing the resolution indefinitely, it is infinite in detail. Mandelbrot realized that this behavior was not a flaw in the measurement. It was a real property of certain shapes, shapes that are irregular in the same way at all scales. Shapes that, if you zoom in on any piece, exhibit the same structure of irregularity as the whole. He called these shapes fractals, deriving the name from the Latin fractus, which means broken, fragmented. And in doing so, he was not just describing a mathematical curiosity. He was naming something that nature had discovered billions of years earlier and was using everywhere. Lungs are fractals. The branching of the bronchi follows a logic of division that repeats on an increasingly smaller scale, from the trachea to the main bronchi, to the smaller bronchi, to the bronchioles, down to the alveoli. This fractal structure allows the lungs to pack a gas exchange area that would correspond to something like 70 square meters inside a volume that fits within the human chest. If the lungs were smooth on the inside, they wouldn't have even a tenth of this capacity. Irregularity is not a defect, it is the solution evolution found to maximize surface area within a limited volume. And the same logic appears in the kidneys, in the small intestine, in plant roots, in river branches, in leaf veins, in the cracks of dry rocks, in snowflakes, in the flames of fire. Snowflakes deserve a paragraph of their own, because the story behind their study is one of the most tranquil and devoted in the history of science. Wilson Alwyn Bentley, born in 1865 in Jericho, Vermont, spent over 40 years photographing individual snowflakes with a microscope attached to a camera he developed himself, protecting each flake from melting with a patience that is hard to imagine. He took over 5,000 photographs throughout his life. What these photographs show, and what anyone with a magnifying glass and a snowy sky can confirm, is that no two snowflakes are identical, but all snowflakes exhibit hexagonal symmetry and a branching structure that repeats in scale. The shape of the flake is determined by the trajectory it took inside the cloud, by the temperatures and humidities it encountered at each altitude in each air current. Each flake is literally a physical record of its own atmospheric history, and this history never repeats exactly. But the physics of water crystallization, which favors 60-degree angles for reasons having to do with the geometry of the molecular bond, ensures that the infinite variety is always contained within a recognizable hexagonal theme. And then there are the rivers. The meanders that Part 3 described in their basic physics become something much richer when life is present on the banks. Riparian trees, those that grow on the banks of rivers, stabilize the banks with their roots, reducing erosion in certain points and allowing it to be more intense in others. When a tree falls into the river, it creates an obstruction that alters the flow pattern, which creates a pool of slow water, which deposits sediment, which creates a higher bank, which is colonized by more vegetation, which produces more trees that eventually fall into the river. Beavers, which are hydrological engineers of extraordinary competence, damming rivers and creating ponds that flood entire valleys, were extinct from much of their historical range in Europe and North America, and where they have been reintroduced, have transformed the landscape in a matter of decades in ways that no human environmental manager could have achieved with the same efficiency. The curvature of rivers that live with beavers is different from the curvature of rivers without beavers. Life sculpts water, and water sculpts land, and land shapes life. Invite yourself now to notice this in your own immediate experience. If you have ever walked through a forest, at some point you must have noticed that the ground is not flat. There are roots that go up and down, depressions where a trunk rotted decades ago, mounds where an animal buried something, small ditches where water drains after the rain. No point on the floor of a real forest is flat for more than a few meters. This irregularity is exactly the fractal of life working on the scale you can traverse with your feet. And if you looked from above, from a height of perhaps 15 meters, you would see how the canopy of a mature forest has the same irregularity, the same mosaic of light holes and dense zones of shadow. And if you looked from 500 meters in an airplane, you would see how the edge of the forest cuts the landscape with a line that is not straight for any stretch, that advances on some hills and retreats on others, that follows rivers and climbs slopes in ways that seem improbable. And if you looked from space, the pattern continues. The same recognizable irregularity at all scales. There are visible forms in nature that most people recognize but rarely have a name for, and naming these forms is a way of making the invisible visible. The logarithmic spiral which appears in the nautilus shell, and the arrangement of sunflower seeds, and the growth pattern of a ram's horn, and in spiral galaxies, is a curve that maintains the same angle with any radius passing through its center. It is a shape that grows, and as it grows maintains its proportion. It is a shape that, in mathematical terms, is scale invariant, of the same family as fractals, but with a regularity that pure fractals do not have. It appears wherever a system grows proportionally, adding material constantly relative to itself. Phyllotaxis, which is the name botany gives to the arrangement of leaves, flowers, and seeds in plants, follows numerical patterns that belong to the Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on indefinitely, where each number is the sum of the two preceding ones. The number of spirals you count on the disk of a sunflower going clockwise is almost always a Fibonacci number. The number you count going counterclockwise is almost always the immediately preceding or succeeding Fibonacci number. This is not coincidence, nor is it magic. It is the consequence of a specific growth mechanism in which each new leaf primordium grows in the place that is furthest from the most recent primordia, and this mechanism, when analyzed mathematically, produces angles that are expressions of the golden ratio, which in turn is intimately linked to the Fibonacci sequence. Nature does not know Fibonacci. It simply grows in the most efficient way, and Fibonacci is the pattern that emerges. Sand dunes are another manifestation that deserves attention because they exist without life and therefore reveal what fluid physics does alone before life amplifies the result. A dune is not just a pile of sand, it is a dynamic structure that moves, grows, divides, and merges with other dunes. The wind transports grains of sand by saltation, which is the process by which grains bounce across the surface, land, and upon landing kick other grains into the air. When this process occurs over a flat surface, the grains distribute evenly. But any small irregularity on the surface captures more grains than the surroundings because it creates a zone of lower wind speed. More captured grains produce a larger irregularity, which captures even more grains. Positive feedback creates a dune where before there was only flatness, and dunes once formed organize into patterns that depend on wind direction. Barshan dunes, which have a crescent shape with the points facing downwind, form where the wind blows from a dominant direction and sand is scarce. Transverse dunes, which are ridges perpendicular to the wind, form where sand is abundant. Star dunes, which have multiple arms radiating from a center and are the highest known, form where the wind varies in direction throughout the year. The wind writes its history in the sand, and whoever knows how to read the shapes of dunes knows where the wind came from and how it varied over the seasons. Ocean waves are another alphabet that most people perceive but rarely decipher. A wave is not water moving from the storm to the beach, it is energy moving through the water. Water molecules describe circles as the wave passes, returning almost to the same place they left. What travels is the shape, not the substance, and this shape, which began as a perturbation created by the wind on a surface, which organized and propagated for hundreds or thousands of kilometers, which arrived at the coast with a regularity that seems impossible given the chaos of its origin, reveals something profound about how order emerges from chaos. The coast does not receive waves. It receives the result of countless perturbations organized by the physics of the water surface into something that has wavelength, period, and direction. And when this wave encounters the shallow bottom near the coast, when the circle the molecules describe begins to scrape the bottom, the wave steepens, slows at the base, and accelerates at the top, and the result is the break, which is one of the most recognizable sounds that exist, and which many people describe as the most naturally relaxing sound they know. This relaxation produced by the sound of waves may have evolutionary roots. The theory, which belongs to the domain of evolutionary psychology and therefore should be received with due scientific humility, is that noises with a fractal frequency, that is, with energy distributed in such a way that at different timescales it presents the same statistical pattern, are perceived by the human nervous system as signals of safe, resource-rich environments. The sound of waves, the sound of wind through leaves, the sound of a stream over stones, all have this fractal frequency structure. There is no pure tone, no straight line in the frequency spectrum. It is the opposite of industrial hiss, which has energy distributed evenly across all frequencies and is perceived as disturbing. Nature, which has no straight lines, also has no sounds with straight lines in its spectrum. And the human nervous system, which evolved within this nature for a period that is almost impossible to imagine, seems still loaded with a preference for the shapes and sounds that indicated in that remote past a habitable world. But there is a point of apparent equilibrium in this story, a zone where all these processes seem to have reached a temporary rest, where positive feedbacks seem to have found their limits, where the landscape seems stable and permanent. A mature forest that has grown and matured over centuries seems permanent. A system of meanders that has stabilized on an alluvial plain seems permanent. A dune field that has found its equilibrium shape with the dominant wind seems permanent. A coral reef that has built its structure over millennia seems permanent. But this equilibrium is an illusion. It is a dynamic equilibrium, not a static one. It is the equilibrium of a cyclist in motion, not a rock on the ground. The cyclist is constantly making small corrections, and if the speed drops below a certain minimum, the equilibrium collapses. In the same way, the systems we described are in equilibrium only as long as the conditions that sustain them remain within certain limits. A forest that seems permanent is one prolonged drought away from collapse. A meander system is one extraordinary flood away from a sudden change of course. A coral reef is a temperature change of a few tenths of a degree away from catastrophic bleaching. And here is the fracture that Part 5 will explore. The apparent equilibrium of natural systems hides thresholds, critical points beyond which the system's behavior changes irreversibly. These points are not visible from within the equilibrium. The system seems stable until the moment it is no longer, and the transition between one state and another is not gradual, not linear, does not obey the intuition that says a small cause produces a small effect. It is abrupt, it is non-linear, and it is in many cases permanent. Thresholds exist in silence. They do not announce their presence. They do not emit signals that the naked eye can easily detect. A system that for decades obeyed certain rules, followed certain rhythms, responded to perturbations with resilience and a return to the previous state, may be accumulating internal tension in a way that no superficial observation would reveal. The stability we see is real, but incomplete. It is the stability of a surface, not of a depth. And when the depth finally moves, the surface has no choice but to move with it in a way that may seem sudden to those who were only watching what was visible. This is the central paradox governing natural systems that avoid straight lines. They are at the same time resilient and fragile. Resilient because they possess compensation mechanisms, negative feedbacks, absorption capacities that distribute the impact of minor perturbations. Fragile because these mechanisms have limits that are not linear. The relationship between the size of a perturbation and the system's response does not follow a constant proportion. A system can absorb 100 moderate-sized perturbations without altering its fundamental behavior. The 101st perturbation of the same size may be the one that pushes the system beyond a threshold that reorganizes it entirely. The scientists who study these phenomena have created a specific language to describe this territory. They speak of tipping points, phase transitions, bifurcations, catastrophes in the mathematical sense, not the colloquial sense. A mathematical catastrophe is not necessarily a tragedy. It is simply a qualitative leap in a system's behavior, a transition between two modes of operation that cannot be reversed simply by undoing the perturbation that caused it. And it is here that human intuition stumbles most often, because human intuition was shaped by linear experiences, by cause and effect relationships that obey predictable proportions. Push lightly, something moves lightly. Push hard, something moves hard. Nature, with its preference for curves and spirals and meanders and eddies, does not operate according to this simple logic. Consider what happens to an air current when it encounters an obstacle. At first, the air flows around the obstacle in a relatively ordered manner, forming flow lines that curve but maintain a recognizable coherence. Increase the airspeed. The flow lines begin to deform more pronouncedly. The pressure at the rear of the obstacle increases. Small oscillations appear. Continue increasing the speed. At a certain point, which can be described mathematically as a function of the velocity, the fluid's viscosity, and the obstacle's dimensions, the ordered flow collapses. Vortices begin to detach alternately from each side of the obstacle, forming a structure that physicists call a von Karman vortex street. The system will not return to the previous ordered flow as long as the velocity remains above this threshold. The transition was irreversible under the given conditions, and the structure that emerged, this alternating dance of vortices, is complex, persistent, and carries energy in a way that the previous ordered flow did not. This vortex street is not just a laboratory curiosity, it is the reason why bridges can enter destructive resonance with the wind. It is the reason why chimneys and towers need certain structural profiles. It is the reason why an airplane's tail experiences specific turbulence at certain speeds. The same principle, the abrupt transition from one flow regime to another, manifests on scales ranging from the microscopic to the planetary. On Jupiter, the Great Red Spot is an anticyclonic vortex that has persisted for centuries, fueled by temperature and velocity gradients between adjacent jet streams. It is a structure that emerged from instability, that organized itself from local chaos, and that has since maintained its coherence in a way that defies intuition. The Earth's atmosphere operates according to the same principles, just with different parameters. Air heated in the tropics rises, cold air at the poles descends, and between these two extremes there are temperature and pressure gradients that the atmospheric system constantly tries to balance. This balancing process is what we call climate, weather, wind. But the system never truly reaches equilibrium because the Earth spins, because the distribution of oceans and continents breaks any symmetry, because the sun heats different surfaces at different rates. The result is a system perpetually far from equilibrium, perpetually generating structures to transport heat from one place to another, perpetually creating and destroying patterns. Hurricanes are the most dramatic expression of this process in tropical latitudes. A hurricane is not born as a hurricane. It is born as a modest atmospheric disturbance, an area of low pressure over the warm ocean, where water evaporation releases latent heat into the air. If conditions are favorable, the moist air rises, the drier, colder air descends around it, and the Earth's rotation begins to imprint a spin on the system. This rotation, in turn, organizes the system in a way that intensifies the central low pressure, which increases the speed of the winds entering at the base, which increases evaporation, which releases more latent heat, which deepens the low pressure even further. It is a positive feedback loop, one of those cycles that amplify themselves until they hit a limit. The limit, in the case of the hurricane, is the ocean surface temperature. As long as the system passes over sufficiently warm water, energy continues to enter the system. When it passes over colder water, or when it hits land, the energy source weakens and the system begins to dissipate. But before that, what has formed is a meteorological machine of enormous sophistication. The eye of the hurricane, this disturbingly calm zone in the center of a circular wind of enormous violence, is the structural signature of a system that has organized itself around an axis of extremely low pressure. There the air descends. Around it, the air rises in a wall of convective clouds tens of kilometers high. The structure is circular, it is symmetrical, it is almost geometric in its perfection, and it was generated entirely by instability, by feedback, by a process that crossed a threshold and reorganized into a qualitatively different mode of operation. Oceanographers observe analogous phenomena in the depths of the oceans. Deep ocean currents, which transport heat and salt in a circuit that takes hundreds or even thousands of years to complete a full cycle, are systems that also possess thresholds. The thermohaline circulation, as it is called, works because cold, salty water is denser and sinks in certain regions of the North Atlantic, creating a movement that is compensated by warmer water coming from the tropics. This system regulates the climate of vast regions. Western Europe is significantly warmer than it would be without it, but climate simulations and paleoclimatic evidence suggest that this system has multiple stable states and that sufficient perturbations, such as a large injection of fresh water from glacial melt, can push the system from one state to another in a way that simply removing the perturbation will not reverse. Geologists find evidence of these leaps in sedimentary records, in the ice of polar caps, in the shells of marine organisms that preserve in their chemical composition the temperature of the water in which they lived. There have been periods when the Earth's climate changed extraordinarily rapidly on scales of decades or even years, alternating between radically different states. These events, which receive names like the Younger Dryas, were probably reorganizations of the climate system that crossed thresholds and settled into new attractors. The linearity we would expect, a gradual warming or cooling proportional to the causes, simply does not describe what happened. The system leaped. Humanity has developed extraordinary instruments to try to observe and measure these processes before thresholds are crossed. Satellites that measure ocean surface temperature with fractions of a degree of precision. Buoys scattered across the oceans recording temperature, salinity, and currents at different depths. Networks of weather stations covering most of the Earth's surface. Doppler radars mapping the internal movement of storm systems in real time. But observation, no matter how sophisticated, faces a fundamental challenge. Thresholds are often invisible from within the system that is about to cross them. The most reliable indicators that a system is approaching a threshold are subtle and statistical, not dramatic and obvious. There is a mathematical phenomenon called critical slowing down that occurs in many systems near thresholds. When a system is well within its stable regime, perturbations dissipate quickly. The system returns to equilibrium rapidly. As the system approaches a threshold, the speed at which it returns to equilibrium after a perturbation begins to decrease. The system seems to become slower in its response, more hesitant, as if it were losing the ability to recover agilely. This slowing down is statistically detectable before the threshold is crossed and represents one of the most promising tools for monitoring systems near critical transitions. Ecologists apply these principles to the study of ecosystems. A lake receiving increasing nutrient loads can remain in a clear water state for a long time with its ecosystem functioning in a recognizable way, but internally the balances are shifting. Algae populations are increasing, biological filters are gradually being overwhelmed. At a certain point, which depends on a whole constellation of local factors, the lake crosses a threshold. Algae explode in a bloom that blocks light, kills aquatic plants, depresses dissolved oxygen, and the ecosystem reorganizes into a turbid eutrophic state that can persist for decades, even if the nutrient load is reduced back to the previous level. The threshold was crossed, and crossing back requires much more than simply undoing the cause. Glaciologists studying the polar ice caps face similar questions. An ice cap covering a topographic elevation has a complex dynamic that includes altitude thresholds. Ice at higher altitudes experiences lower temperatures and loses mass more slowly. If the ice cap begins to shrink, its average altitude decreases, exposing the remaining ice to higher temperatures, which accelerates melting, which further decreases altitude in a self-feeding loop. This mechanism, called the altitude mass feedback, can be the trigger for relatively rapid disintegrations of ice caps that seemed stable. Models suggest that certain ice caps have thresholds beyond which this dynamic becomes dominant and collapse is irreversible on human timescales. While you rest somewhere over the tropical Atlantic, a cluster of convective storms is evaluating through the pure mechanics of fluids and pressure gradients whether conditions are sufficient to sustain the organization that turns perturbation into a system. The ocean beneath it has a specific temperature, which is being calculated by satellites passing 500 kilometers above. The humidity of the air, the wind shear at different altitudes, the exact location of the disturbance relative to the equator, all this is being processed by the system itself, not consciously but mechanically and inevitably. According to the equations governing fluid motion in rotation, the system is at this moment on the inside or the outside of a threshold, and this distinction, invisible to the human eye, will determine whether that modest disturbance will quietly dissolve into the ocean in the coming days or whether in 2 weeks it will be over a coast with circular winds of enormous speed, reorganizing the environment according to the logic of its internal structure. The mathematicians who developed bifurcation theory, which is the formal language to describe these transitions, realized that thresholds have a geometry of their own. In an abstract space where the system's parameters are the axis, thresholds form surfaces that separate regions of qualitatively different behavior. Crossing these surfaces is changing regions, and the shape of these surfaces determines whether the transition is smooth or abrupt, reversible or not, local or global. René Thom's catastrophe theory classified the types of simplest threshold surfaces and found a surprisingly small number of fundamental shapes, suggesting that the qualitative leaps we observe in nature obey a typology that can be studied and, in principle, predicted. But prediction runs into another fundamental property of these systems: sensitivity to initial conditions. Nonlinear systems that are far from equilibrium, precisely the systems that generate the curved, spiral, and vertical structures we explored in previous parts, tend to be extraordinarily sensitive to small differences in starting conditions. Differences that would be negligible in a linear system become exponentially amplified in a non-linear system, separating trajectories that began almost identically. This does not mean the behavior is random or incomprehensible. It means it is chaotic in the precise technical sense, deterministic in its mechanisms, but unpredictable in its specific details beyond a certain time horizon. The forecasting horizon for atmospheric weather is about 2 weeks at the current state of science and technology. Beyond that, the differences that models cannot capture in the initial conditions, differences smaller than any instrument can measure, grow to dominate the predicted behavior. This is not a technological limitation that will be overcome with faster computers or more measuring stations. It is a fundamental mathematical property of the system we are trying to predict. The atmosphere is a chaotic system, and chaotic systems possess intrinsic predictability horizons. Within this horizon, we can make useful forecasts. Beyond it, we can describe probabilities, climatologies, envelopes of possibility, but not specific trajectories. And there is a profound irony in this limitation. The same properties that make these systems unpredictable in their details are the ones that make them so rich in structure and so capable of generating patterns of a complexity that goes far beyond what the initial conditions seem to contain. The nonlinearity that amplifies small differences and scrambles trajectories is the same nonlinearity that allows the formation of coherent structures, persistent vortices, organized currents, patterns that repeat without ever being exactly identical. Chaos and order are not opposites in this territory. They are complementary expressions of the same underlying mathematics, which is the mathematics of systems that prefer curves to straight lines, that find in meanders and spirals and eddies the ways the universe manages its internal tensions. Rivers, whose meandering behavior we explored in detail earlier, also have their moments of dramatic intensification. An extraordinary flood can, in a matter of hours, cut through a meander that took centuries to develop, creating a straighter course and leaving behind a crescent-shaped lake called an oxbow lake. The fluvial system leapt from one state to another. The abandoned meander, and the new course briefly coexist on the terrain, but they are testaments to different regimes, a before and an after separated by a flood that crossed the threshold beyond which the river could not maintain its previous path. And the new course, over time, will begin to meander again, because the forces that produce meanders have not disappeared. They were just temporarily overcome. This persistence of underlying tendencies, this return of patterns, even after events that temporarily erased them, is one of the most consistent observations in the study of natural systems. Patterns are not just results of the process. They are expressions of properties the system possesses independently of momentary conditions. A river on a plain meanders because the physics of moving fluids over deformable surfaces produces meanders. A perturbation can alter the specific geometry of existing meanders, but it cannot alter the physics that produces them. In the same way, the convection currents that produce hexagonal cells inside a heated liquid, the spirals that emerge in oscillating chemical reactions, the vortices that form behind obstacles, all are expressions of physical properties that will continue to generate these patterns as long as the general conditions that sustain them are present. What dramatic phenomena reveal then is not a rupture with the previous order, but a transition to a different expression of the same order. The intensity is greater, the speed of transformation is greater, the effects are more visible and often more destructive. But the principles governing the intense behavior are the same that govern the calm behavior. It is the same fluid physics, the same equations of conservation of mass and momentum and energy, the same feedback mechanisms. The difference lies in the values of the parameters, in the system's position relative to its thresholds, in the amount of energy available to be organized and expressed. And these phenomena, no matter how dramatic in themselves, do not happen in a vacuum. A tropical storm forming over the Atlantic alters atmospheric conditions in regions thousands of kilometers away. A flood reshaping a fluvial delta changes the coastal morphology that influences local marine current circulation. An ocean warming episode that causes coral reef bleaching alters wave patterns reaching adjacent coasts, because the reef no longer exists as a three-dimensional structure that dissipated wave energy. Phenomena are interconnected in ways that extend far beyond their apparent boundaries. Every intensified system sends signals to others, alters parameters that matter to other systems, contributes to conditions that another system elsewhere is evaluating against its own thresholds. Every system that coils, that spirals, that pulses in unequal rhythms exists within a vast network of exchanges. There is no curved system that is truly isolated. What happens in a cold water eddy in the South Pacific resonates in rainfall patterns over northeastern Brazil months later. What happens in a jet stream deforming over the Arctic determines whether a heat wave will settle over Central Europe for days or weeks. Curvature is not just a property of individual objects. It is a language systems use to talk to each other, a vocabulary of shapes that carries information across scales that human intuition rarely manages to embrace all at once. The deepest partner the universe of curved shapes has, the system with which it exchanges energy and information in the most intimate and consequential ways, is the flow of time itself. This may seem like a strange statement at first reading because we tend to think of time as a stage where events happen, not as an active participant in exchanges between systems. But consider what it means for a vortex to exist. A vortex is not an object, it is a process. It is a temporary organization of matter and energy that remains coherent because it continuously processes differences in pressure, velocity, temperature. Remove the flow of time and the vortex does not freeze in some static position, it simply ceases to be what it is. The curved shape and the temporal process are inseparable in a way that goes beyond simple dependence. What makes this exchange between form and time especially rich is that it operates in directions that are not symmetrical. A cyclone forming today over the Indian Ocean was made possible by conditions that accumulated over weeks, ocean temperatures that gradually rose, high-altitude winds that positioned themselves favorably, an initial disturbance that existed as an almost imperceptible asymmetry in the atmosphere before it began to be amplified. The system's history is inscribed in its present structure in ways that only a highly trained eye can read. And what the system does now alters the conditions for what will exist later. Time does not just allow the shape to exist. The shape modifies the time that succeeds it, leaves marks on the future states of the system that contains it. This leads us to one of the most fascinating questions that emerge when studying the universal curvature of physical phenomena: how feedback loops work when what is being fed back is the system's own propensity to produce curvature. Oceans cover more than 70% of the Earth's surface. They absorb enormous amounts of heat and carbon dioxide. When oceans warm, the currents circulating within them change behavior. Currents that were stable and well-defined begin to oscillate with greater amplitude, develop larger meanders, produce more energetic eddies that detach from the main currents and travel hundreds of kilometers before dissipating their energy in the colder ocean around. Each of these ocean eddies is a curved structure that exists for weeks or months, that mixes waters of different temperatures and salinities, that alters conditions for marine life over an area much larger than its own immediate extent. When researchers measured the population of large ocean eddies over decades using satellites that detect the gentle elevations and depressions on the sea surface these eddies create, they found a trend that confirmed what physical models predicted. As the ocean warms, the population of eddies changes, not necessarily increasing in absolute number dramatically, but the eddies that exist tend to be more persistent, carry more energy, move in ways that interact with the main currents more complexly. A warmer ocean is an ocean where curvature is, in a sense, more exuberant. The extra heat fuels the instabilities that produce the eddies, which in turn redistribute heat in ways that create new instabilities elsewhere. This cycle has a disturbing elegance. Warming produces more eddies. Eddies redistribute heat in ways that sometimes amplify warming in specific regions. Amplified warming in specific regions affects the atmosphere above those regions. The affected atmosphere develops its own modified circulation patterns. These modified atmospheric patterns in turn affect how heat is exchanged between the atmosphere and the ocean in places that may be very far from the point of origin. The signal circulates, transforms, appears in new contexts. It is the same kind of feedback we see in river meanders, but operating on scales of space and time that challenge human ability to trace causes and effects precisely. The short-term behavior of these systems, what happens in years or decades, is in many ways easier to document than to explain. We can measure with a reasonable precision that the extent of Arctic ice at the end of summer has consistently decreased over the last few decades. We can measure that the ice that remains is on average younger, thinner, more vulnerable to seasonal melting than the ice that dominated the region decades ago. We can measure that the boundary between Arctic air and mid-latitude air, which was once sharper and more stable, has become more diffuse, more undulating, more prone to developing deep meanders that push cold air far south and pull warm air far north. All this is measurable, but the chain of connections between each of these observations and the others is complex enough that the precise attribution of cause and effect is an active field of research full of technical controversies. Long-term behavior, what happens over centuries or millennia, adds an extra layer of complexity. The curved systems that dominate the Earth's surface and atmosphere have long memories. The deep ocean below a few kilometers of depth contains water that may have been out of contact with the atmosphere for centuries. This water carries records of climatic conditions that existed when it last sank, when the cold and salinity of the surface at a certain point in the North Atlantic or the Southern Ocean made it dense enough to begin its slow descent to the bottom. The thermohaline circulation system, the great conveyor belt that moves water through the world's oceans in circuits that take centuries to complete a full cycle, is a global-scale curved structure, a flow that meanders through connected oceans carrying heat, salt, nutrients, dissolved carbon. When paleoclimatologists study sedimentary records from the ocean floor, they find evidence that this global circulation is not a constant. It can weaken, reorganize, even undergo abrupt transitions to fundamentally different states. During some of the glacial periods of the deep past, it seems the deep Atlantic circulation functioned in ways significantly different from what we observe today. The consequences for global climate were substantial. Regions that are temperate today became much colder, while other regions responded in less intuitive ways. The system didn't just get colder everywhere uniformly. It reorganized, developing new circulation configurations that created new patterns of temperature, precipitation, ice distribution. This places us before one of the most unsettling frontiers of contemporary scientific knowledge. We know these systems have the capacity for abrupt reorganization. We know some of them have threshold points beyond which a state becomes unstable and the system can rapidly collapse into an alternative state. What we do not know with satisfactory precision is where these thresholds are, how close we are to them at any given moment, and what exactly would trigger a transition. This uncertainty is not the result of simple ignorance that more research will necessarily solve. It reflects something deeper about the nature of chaotic systems, which is the extreme dependence on initial conditions. The dependence on initial conditions is a principle that was formalized mathematically in the last century and illuminates something that practitioners of any science dealing with complex systems already felt intuitively. For a system that exhibits sensitivity to initial conditions, two states that begin arbitrarily close to each other can diverge exponentially over time. This is not just a technical measurement difficulty, it is a fundamental property of the dynamics of these systems. The American meteorologist Edward Lorenz arrived at this understanding memorably when, trying to repeat a computer simulation of atmospheric patterns, he entered the initial data with one less decimal place than in the original simulation and saw the result diverge completely after a certain number of simulated time steps. The image that became associated with this discovery, the idea that the flap of a butterfly's wings in Brazil could in principle alter whether a tornado forms in Texas weeks later, is obviously a poetic hyperbole. No specific wing flap specifically causes any specific tornado, but what the image captures is real. For sufficiently sensitive systems, initially minuscule perturbations are amplified by the system's own functioning until they become macroscopic differences in the outcome. For these systems, there is a predictability horizon. Beyond a certain future time, any forecast based on initial conditions not known with arbitrary precision becomes essentially random relative to what will actually happen. For the Earth's atmosphere, this horizon is around 2 weeks, not because our technology is insufficient, although it can certainly improve, but because the system itself amplifies the inevitable inaccuracies in any real measurement faster than our ability to make compensatory measurements. This does not mean nothing beyond 2 weeks can be predicted. It means specific weather forecasts. It will rain in this city on this specific day lose validity quickly. But climate forecasts of long-term average behavior, of statistical trends in the distributions of extreme phenomena, these are statements about different properties of the system, properties that are not subject to the same kind of explosive amplification of initial errors. It is a subtle but fundamental distinction. Climate is, in a sense, more predictable than weather, not because it is simpler, but because we are asking different questions about the system. Asking what will the exact temperature be at noon in a given city on the 14th day of next month is asking about a specific trajectory of the system. Asking how will the frequency of intense tropical cyclones be distributed in the next decade is asking about statistical properties of the set of possible trajectories, about the state space the system visits more or less frequently. This second question, while still difficult and subject to considerable uncertainties, does not suffer from the same explosive amplification of initial errors. But even with this distinction in mind, there are profound limits to what we can know about the systems around us, and these limits are not just practical, they touch on something philosophical about the relationship between observer and observed system, about what it means to know a system that is complex enough that any partial description of it is necessarily a simplification that omits something consequential. The best models we build to simulate global atmospheric and oceanic circulation are impressive works of intellectual engineering. They correctly capture an enormous variety of phenomena. They predict patterns that subsequent observations confirm. They allow us to explore how the system would respond to perturbations we have not yet experienced. And at the same time, all of them simplify. All of them represent the ocean as a grid of finite dimensional cells, when the real ocean is continuous and possesses structures on all scales between the molecule and the entire ocean basin. All of them parameterize processes that occur on scales smaller than the grid resolution, using equations that capture the average effect of these processes, but not their specific variability at each point and moment. These simplifications are necessary. They are not failures of scientists' imagination. The real system simply contains more degrees of freedom than any conceivable computer could simulate explicitly. We are always and inevitably working with representations that are faithful to the essential but omit the detail. There is something profoundly human about this situation. We are medium-sized creatures of average lifespan relative to the scale of the cosmos, endowed with senses that capture only a slice of the spectrum of physical phenomena that exist, building instruments to extend these senses and reasoning to extend our intuition, trying to understand systems that exist on scales of space and time we could never experience directly. And yet we understand something genuine. Not everything, but something real and profound about how these systems work, about why they curve instead of progressing in a straight line, about the instabilities that make them alive and dynamic. This partial understanding has a quality that goes beyond the merely instrumental. There is a specific beauty in contemplating a system that is at the same time governed by laws we can state clearly and surprising in its particular behavior in ways we did not predict. A vortex in a cup of coffee does not violate any physical law. Every water molecule in it follows equations of motion we can write down. And yet the specific vortex that forms on a specific day with that precise curvature, that rotation speed, that depth, is singular and unrepeatable. The laws are universal. The manifestations are particular and inexhaustible. This tension between the universal and the particular is perhaps what makes the study of curved systems so persistently fascinating. It is not just that the phenomena are aesthetically beautiful, although they are. It is that they visibly embody a duality that runs through all physics, all science, perhaps all human attempt to understand the world. There are patterns that repeat, there are principles that govern, there is something regular and predictable in the deep structure of things, and at the same time the specific is always richer than the general law, always contains something the law does not completely capture. always surprises the observer who has settled too comfortably into the familiarity of general principles. And when we slow down before this reality, when we stop trying to catalog the phenomena and simply contemplate them for a moment, something reveals itself that is difficult to articulate in technical language. There is a kind of coherence underlying all this diversity of curved shapes. The spiral of a galaxy and the spiral of a cyclone and the spiral of a mollusk shell are not made of the same material nor operate by the same immediate mechanisms, but there is something in common between them that goes beyond the superficial similarity of shapes. There is something that generates them, some principle deeper than any of the specific mechanisms that produce each of them, that makes the universe in radically different scales and contexts arrive at shapes that look alike, that obey the same proportions, that coil in the same direction relative to the forces that produce them. This something is not a mystery in the sense of being impenetrable to thought. It is accessible, it can be approximated, it can be described with increasing precision as understanding advances, but it has the peculiar quality of being easier to feel than to completely formulate in a single statement. It is as if the entire enormity of curved shapes the universe produces, from eddies in the atmosphere to the trajectories of planets, from ocean currents to galactic spirals, were variations on a theme we have not yet been able to state in its totality, a theme that each new discovery partially illuminates, but which remains richer than any description we have yet made of it. Feedback is one of the most silent and yet most powerful principles the universe employs to ensure that curves are not accidents but destinies. When a river begins to curve, even if for a small reason, a displaced stone, a minimal difference in soil density, the curvature itself becomes the cause of the next curvature. The water rounding the outside of a curve moves faster, erodes the outer bank more, deepens the curve, increases the velocity difference, and so the process feeds itself with a fidelity that seems almost intentional. There is no planner, there is only a process that found a way to perpetuate itself, and in perpetuating itself, sculpts the world with a patience no conscious will could sustain. This type of feedback that amplifies is called positive by physicists and systems dynamics scholars, and the name is misleading because positive sounds favorable, while what it describes is simply a loop where the effect returns to the cause and intensifies it. The eddy that begins to spin attracts more fluid to its center, and by attracting more fluid spins faster, and by spinning faster attracts even more. The storm born over the heated ocean absorbs moisture, and by absorbing moisture releases latent heat, and by releasing latent heat becomes more intense, and by becoming more intense aspirates more moisture. The galaxy that begins to rotate concentrates stars in the spiral arms, and by concentrating stars creates regions of greater gravity, and by creating regions of greater gravity curves the orbits of neighboring stars more, deepening the arms, making the spiral sharper, more robust, more lasting than any shape that could have emerged from a force applied just once and forgotten. But if the universe contained only amplifying feedbacks, everything would soon become chaotic beyond any recognition. What allows spirals to be beautiful, eddies to be stable long enough to be seen, orbits to repeat over eras, is the simultaneous existence of feedbacks that stabilize, which physicists call negative, and which function as memory embedded in systems, a tendency to return to a state of equilibrium when excessively perturbed. A planet's orbit is maintained not because gravity is constant in intensity, but because when the planet gets too close to the Sun, gravity pulls it inward harder, but the increased orbital speed throws it outward even harder, and the two effects balance in a cycle that is not rest but a continuous dance around an equilibrium that is never reached and never lost. It is the coexistence of these two forms of feedback that allows the universe to be simultaneously dynamic and recognizable. Living systems are perhaps the most elaborate examples of this coexistence. A cell maintains its temperature, its salt concentration, its chemical balance through dozens of negative loops that continuously correct any deviation. But at the same time, the processes that allow the cell to grow, divide, respond to stimuli depend on positive loops that amplify small signals into large responses. Life did not choose between stability and change. It learned over billions of years of trial and elimination to use them simultaneously in different proportions, depending on the moment, the context, the need. And curves are in all these dynamics, not as ornament, but as the shape loops take when expressed in space and time. A feedback loop is literally a loop, a curvature that returns to the starting point, modified by the path traveled. The spiral patterns we see in meteorological systems, biological systems, galactic systems are the spatial signature of processes that fold back on themselves in time. When the cause returns to the effect it generated, the system writes its history in curves. The molecular dimension of this story is perhaps the most intimate of all, because it is the dimension where the geometry of curvature begins not in the large visible processes, but in the invisible architectures of the substances that make up everything. Molecules are not balls connected by rigid sticks. They are clouds of electronic probability, regions where electrons spend more time and regions where they spend less, and these distributions create geometries that determine everything about how molecules behave, how they pack, how they fold, how they interact with water and light and other molecules. The water molecule is curved. The angle between the two hydrogen atoms and the central oxygen atom is not 180 degrees, which would create a straight line, but 104.5 degrees, which makes the molecule a sort of microscopic boomerang. This geometric detail, this small curvature embedded in the most fundamental structure of the liquid that covers most of the earth and makes up most of living beings, is responsible for practically all the extraordinary properties of water. The surface tension that allows insects to walk on rivers, the ability to dissolve substances of diverse polarities, the anomalous density of ice, which makes it float instead of sink and therefore allows lakes not to freeze from the bottom up and exterminate aquatic life in winter. All this, everything emerges from the curvature of a molecule of 18 atomic mass units. Proteins are longer stories about the same issue. A protein begins as a linear chain of amino acids, a sequence of units connected in a row. But the linear chain is just the draft. The real story begins when the chain starts folding onto itself, guided by the interactions between amino acids that are close in the sequence and those that are far apart, but folding brings together. The final result, after milliseconds of exploring the space of possible shapes, is a unique, specific three-dimensional structure with cavities and protrusions and curved surfaces that fit into other molecules with a precision that seems impossible for something so small. The function of a protein is almost entirely determined by its shape. An enzyme that breaks a chemical bond has in its active site a curved geometry that embraces the substrate in just the right way to weaken exactly the bonds it needs to break. A receptor on a cell's surface has a curved recess that accepts only molecules with the complementary shape, like a lock that only opens with the specific key. Hemoglobin has a structure that changes shape when transporting oxygen and when releasing it, a conformational transformation that is the mechanism by which oxygen is efficiently carried from the lung to the tissues. Molecular curvature is not decoration of function, it is the function. DNA is perhaps the most iconic example of curvature in the molecular dimension. The double helix is a spiral, and this shape is not arbitrary. It emerges from the need to pack two complementary strands so they can be separated for reading and replication. held together by forces specific enough to ensure information fidelity, and organized so that packing 2 meters of length inside a nucleus of a few millionths of a millimeter is possible. The helix is the solution evolution found for this set of constraints, and it is a solution so efficient that essentially all life on Earth uses it. When the universe is viewed as a system and not as a collection of separate objects, the absence of straight lines ceases to be a curious observation about the shape of things and becomes an emergent property of the very way systems function. A system is a collection of interacting parts, and the interactions create influences that propagate between the parts. When one part changes, it affects other parts, which affect still others, which eventually return to affect the original part. This circular flow of influences is the essence of systemic behavior, and it inevitably produces dynamics that do not follow straight lines, because straight lines are the special case where each cause has only one effect and each effect has only one cause, and real systems are woven from mutual causes and effects that intertwine in patterns only curved geometry can describe. Emergence is the phenomenon by which these interactions produce patterns that were not present in the individual parts and could not have been predicted from studying the parts in isolation. No single water molecule has temperature, but a collection of many water molecules has temperature. No single neuron thinks, but a collection of many neurons connected in certain ways thinks. No single subatomic particle is alive, but collections of particles organized in certain ways are alive. Emergence is not magic, but it seems like magic because the distance between the ingredients and the result is enormous, and the path from one to the other passes through a wealth of interactions that no mind can fully trace. Curves emerge in the same way. No single water molecule knows it should circulate in eddies, but collections of many water molecules, subject to temperature and pressure gradients and the Earth's rotation, circulate in eddies with a regularity that seems deliberate. Galactic spirals were not drawn. They emerged from the gravitational interactions of billions of stars over billions of years, each star following only the forces it felt at the moment, with no awareness of the global shape it was helping to create. The beauty of the universe's curves is the beauty of emergence, the beauty of patterns that are greater than any of their parts and arise spontaneously when the right conditions meet. Deep down, the absence of straight lines in the universe is simply the geometric expression of the fact that nothing exists in isolation. A straight line is the trajectory of something unaffected by anything around it, but the universe does not offer this isolation. Everything feels the presence of everything around it. Gravity reaches infinitely. The electromagnetic field reaches infinitely. The weak and strong forces shape the interior of every nucleus. And when everything affects everything, trajectories cannot be straight, because being straight would mean ignoring all lateral influences, and nothing in the universe can do that. Curvature is the mark of a cosmos where parts are not indifferent to each other, where the presence of each thing modifies the trajectory possibility of everything else. Every galaxy spiral then is not just a pretty shape in a telescope. It is proof that stars that never touched, separated by light years of vacuum, know each other gravitationally and organize their trajectories relative to each other over eras. Every eddy in the ocean is proof that water molecules distant from each other communicate through pressure and temperature and together create a dance none of them would execute alone. Every DNA helix is proof that information, to be preserved and transmitted across generations, needs to embrace itself in a spiral, fold onto itself so the two strands protect and complement each other. The universe does not hate straight lines out of caprice. It avoids them because straight lines would be the signature of a cosmos of isolated parts, and the cosmos that exists is a cosmos of parts that ceaselessly affect each other. Curvature is the language of connection. It is the shape, space, and time and matter found to show they are, all of them, in permanent conversation. Every curve we see is a sentence in this conversation, an instance where something changed its direction because of something else, and in changing wrote the history of that influence in space. The oceans that surrounded this planet for billions of years, the winds that swept their surfaces, the currents that carried heat from the tropics to the poles, the cyclones that redistributed energy across the globe, all this was writing curves because it was doing exactly what the universe does on all scales. It was responding to the world around it. It was being affected and affecting, receiving and transmitting, bending under influences and bending influences around itself. When you close your eyes now, the universe continues. Galaxies spin in their spirals with a slowness so vast no human life would perceive the slightest arc of their movement. Planets trace their ellipses with the regularity of a clock that never needs adjusting because it was adjusted by gravity before there was a word to describe anything. Oceans circulate in their silent gyres, carrying heat, carrying salt, carrying the chemical memory of eras that predated anything we can call history. The clouds above you, if there are clouds, organize into spiral patterns that obey the same geometry that organizes continental storms and ocean cyclones. Because the rules governing the air are the same on all scales, and the air does not know you are looking or not looking. It spins because the earth spins, and the air moves and heat rises and pressures differ, and the result is always curves, always spirals, always the same geometric signature of the universe in conversation with itself. Inside you, the blood traces its own curves. The heart pulses, and the blood departs in waves that are not straight lines but pressures propagating through tubes that branch and curve and branch again, each branching calculated by billions of years of selection to minimize work and maximize reach. The oxygen molecules detaching from hemoglobin do so because the protein changed shape, because a molecular curvature transformed into another molecular curvature, and this microscopic movement is what allows every cell in your body to keep breathing while you rest. You are made of curves. You live in curves. You move through a cosmos that never offered a straight line to anything that existed. And this, far from being a limitation, is proof that you belong to a universe where nothing is indifferent to nothing, where every trajectory is shaped by presences, where to exist is to be affected and to affect, to curve and to be curved. Let this perception settle softly. You are safe within the curvature of the world. The universe takes care of you with the same gravitational attention with which it cares for every planet in its orbit. Everything is in order, in the same spiral order that has always organized the stars. While you rest, galaxies continue to spin. While you rest, oceans continue to circulate in their silent gyres. While you rest, the DNA inside every cell of your body remains coiled in its faithful helix, guarding the information that makes you you. You are part of this. You always have been. The same physics that coils nebulae into spirals coiled the proteins that built your body. The same force that bends light around stars bends the air you breathe around every obstacle. You are not separate from the pattern. You are the pattern in one of its most improbable and most wonderful forms. Let the weight of the body rest now. Let thoughts lose their straight edges. Let the breath find its curved rhythm, its expansion and contraction, its small, faithful tide. The universe doesn't need straight lines, and you don't need them now either. You are safe. The universe takes care of you. Everything is in order. The spirals continue to spin softly as you depart towards sleep. The curves of the cosmos close around you like an embrace that existed before you were born and will continue after you wake. Good night. The universe continues its silent dance, and we rest in its embrace. Thank you for walking with me tonight. Sleep well.